Welcome to the college-level Kinematics lecture deck, where we explore the science of motion from first principles to advanced applications. Over the next slides, we'll build intuition about how objects move, learn essential equations, and see how these ideas apply in labs, simulations, and real-world systems. Think of this as a guided tour through the language and tools of motion analysis. This table of contents outlines our roadmap. We start with basic definitions, then cover core quantities like position and velocity, move into constant acceleration and graphical analysis, and continue through projectiles, rotation, and relative motion. Later sections introduce experimental methods, computational modeling, robotics applications, educational tools, biomechanics, advanced topics, and wrap up with assessment and review. Kinematics studies motion without worrying about the forces that cause it, focusing instead on where things are and how fast they move. That's different from dynamics, which brings forces into the picture. The classroom image reminds us this course blends theory with examples, so we'll emphasize clear definitions and practical reasoning to build a solid foundation for solving motion problems. Here we introduce the fundamental quantities you'll use again and again: position as a location, velocity as the rate of change of position, and acceleration as the rate of change of velocity. Both velocity and acceleration are vector quantities, so direction matters. The visuals, including a car diagram and position measurements, help connect these abstract ideas to measurable motion in 1 and 2 dimensions. When acceleration is constant, a compact set of equations gives us powerful predictive tools. One for final velocity, another for displacement over time, and a third that relates velocity to displacement without time. These formulas let you solve many one-dimensional motion problems quickly, and the box summaries on the slide show the relationships you'll use in problem solving and checking your work. Graphs are a key way to interpret motion. A position time plot shows where an object is and yields instantaneous velocity from its slope, while a velocity time graph makes acceleration obvious from slope and gives displacement from the area under the curve. Acceleration time graphs highlight constant or changing acceleration directly. Reading slopes and areas turns visual data into quantitative insight. Projectile motion breaks two-dimensional motion into independent horizontal and vertical parts, which simplifies analysis significantly. The horizontal component has no acceleration if we ignore air resistance, so horizontal velocity stays constant, while the vertical component is governed by gravity, causing a constant downward acceleration and changing vertical velocity throughout the flight. As illustrated by the trajectory image, rotational kinematics mirrors linear motion using angular variables. Angular position, angular velocity, and angular acceleration behave like their linear counterparts. You can convert between linear and angular quantities using the radius, and arc length equals radius times angular displacement. The slide's visuals and the classroom photo help link these angular concepts to rotating systems and everyday examples. Relative motion depends on the frame of reference you choose, so observers in different frames can describe the same motion differently. We use vector addition to combine velocities from multiple frames and build accurate kinematic descriptions for complex situations like moving platforms or boats in currents. The images on this slide emphasize perspective, reference frames, and how to assemble velocities logically. A systematic problem-solving approach makes kinematics manageable. Start by sketching a clear diagram with labeled axes, then list knowns and unknowns to guide your plan, and finally choose appropriate equations while checking units and assumptions. Treat each step deliberately and verify results against physical intuition to avoid common mistakes and ensure your solutions are consistent and reproducible. Experimental kinematics uses sensors and video analysis to collect real-world data on position, velocity, and acceleration, as shown in the lab photos. Careful data collection is paired with error analysis and validation techniques to quantify uncertainty and ensure measurements are reliable. By combining experiments with theoretical models, we test assumptions, refine predictions, and gain confidence in our conclusions. Computational modeling offers numerical tools for studying motion when analytical solutions are difficult. The Euler method updates position and velocity in small time steps to approximate motion, and simple programs can simulate complex trajectories and non-constant acceleration scenarios. These techniques are versatile, supporting projectile problems, oscillatory systems, and exploratory simulations that deepen conceptual understanding and practical skills. Kinematic principles play a central role in robotics, from cable-driven mechanisms to serial and parallel manipulators, shaping how we predict end effector motion and design control strategies. Advanced methods like multi-objective optimization, balance speed, accuracy, and other performance criteria, and these concepts are essential for creating and tuning modern robotic systems across industrial and research applications. Educational technology and interactive simulations enhance learning by making abstract kinematic ideas tangible. Tools like PhET provide dynamic visualizations that help students build conceptual understanding, while guided tutorials and hands-on simulations improve outcomes by linking theory to experimentation. Integrating these resources into instruction boosts engagement, clarifies misconceptions, and supports deeper, more resilient learning. In biomechanics, kinematic analysis helps us study human movement through gait cycle evaluation and joint motion quantification. Measuring angles, velocities, and accelerations provides data on movement efficiency, stability, and joint health, which is useful for clinical diagnostics and ergonomic design. The lab imagery highlights how motion capture and careful analysis bring kinematic tools into applied human motion studies. Looking ahead, we preview advanced topics that extend kinematics into complex regimes. Non-inertial frames introduce fictitious forces like centrifugal and Coriolis effects, and relativistic kinematics touches on time dilation and length contraction at high speeds. These concepts show the limits and extensions of classical kinematics and point toward deeper studies in dynamics and modern physics. To wrap up, assessment and review focus on conceptual questions that address common misunderstandings and a set of sample problems ranging from one-dimensional motion to projectile scenarios. Working through these exercises reinforces your grasp of core concepts, sharpens problem-solving skills, and prepares you to apply kinematic reasoning in both theoretical and experimental contexts.